talked about linear transport equation, and now let's talk about linear homogeneous equations in two variables. And linear, what we call the one-dimensional equation, is just in this family of equations. It's an example of this linear homogeneous equation, right? So just when we consider it one-dimensional case. So here we have just this equation. Z here is the unknown function, the function that we would like to find. X and y are independent variables, and we assume that functions f and g, coefficients in our equation, are continuous function in some domain where variables, independent variables x and y, are changing. And if we introduce these Monge notations, p is dz dx and q dz dy, then our equation, let's give it number 1, this our equation 1 can be rewritten in this form: f times p plus g times q equal 0. And then consider this set of 5 numbers, this fifth tuple. And we can call it plane element or tangent element. And consider a corresponding plane in the space R3, space where our variables x, y, and z are changing. And you can see that this is equation of plane, right? And we can see that point x0, y0, z0, this point belongs to this plane, and so this is a point in the plane, and p sub-0, q sub-0 we will call direction elements. And so now what happens if we just fix this point x0, y0, z0, just if it's a fixed point, then what happens to our plane if we will be changing p0 and y0? If we will be changing, we will be, our normal to the plane will be changing, and we will obtain a bundle of planes, so it will be many planes. And here we will exclude the plane that is orthogonal to our x or y. So suppose that here we have, so three-dimensional space, we have x or y plane where x and y are changing, right? Z is our function of x and y. And we can draw a picture. So if we assume that z is function of x and y, and it is continuous, it will give us continuous differentiable surface. So we assume that it's continuous differentiable surface in the space. And then the plane element, if we take x, y, c, cx, and cy, defines a tangent plane to our surface for any point x, y in D. And so this would be equation of this tangent plane. So the corresponding picture would be, so if we take this, our coordinates, right? So we have x, y, and z. And then if we draw our surface, and so if this is our surface z equal c of x, y, then on this surface we can take a point with coordinates x0, y0, z0, right? That would be our point. and normal so suppose we just want to draw a tangent plane here at this point, through the point x0, y0. This would be our tangent plane, right? And normal to this tangent plane would be expressed on psi-x, psi-y, and -1, right? So the normal will be, it will be psi x at x0, y0, psi y at x0, y0, and the third component would be -1. Right? So I will write it here again. So m is this vector psi x, x0, y0, then psi y, x0, y0, and -1. So this is our normal vector. Okay, so now recall our main equation, one written in this form or in this form, right? Fp plus gq equals 0. And due to this equation, we can assign a plane element to each set of x sub 0, y sub 0, z sub 0, p and q, right? So for any just point x0, y0, z0. And we can assign this plane element such that our p and q satisfy this equation, but since we took this point, that will be f at x0, y0, p plus g of at x0, y0, q. And everywhere we assume that functions f and g are not simultaneously 0, right? So we can take norms, or we can put just squares. So we put that their sum is greater than 0, meaning that they are not simultaneously 0, otherwise there is nothing to say about our equation, it will degenerate. and then we will obtain a bundle of planes, except for the plane that is perpendicular to our plane x or y, because we don't want, we want our surface to be continuously differentiable surface. And I claim that these planes, all these planes that we can assign, contain a horizontal line. So you see this parametric representation of this line. T here is a parameter, and the line you can see passes through the point x0, y0, z0. And then you can see why it is a horizontal line, because z is a constant here. And how we can see that this is really true, then this is our equation, right, that we had here. So I replace here psi-x with p and psi-y with q. So this is our equation. And then if I replace from here x minus x0 with f at the point times t, right? And y minus y0 with g at the point x0, y0 times t, and yeah, I plug for z, I plug z naught, then equation, and then I will pull out t, and then equation will become pf plus qg, and that if we said that pq satisfies this equation, then we have 0, so we can see that our planes have this horizontal line. So if I want to draw it, then here are our coordinates x, y, and y and z, and if we have somewhere point x0, y0, z0, somewhere this point from that surface, then we can draw this bunch of planes. That would be one plane, another plane would pass, would have the same line, but it will say will be this plane. I don't know how to draw it, that's another plane. So we have a bunch of planes except for the plane that is perpendicular to this one, so we will have this bundle of planes that have a horizontal line. And so this bundle of planes is called Monge bundle. So geometrically, integral of our equation 1 is any continuously differentiable surface z as a function psi of xy. So any continuously differentiable surface such that at every its point z0, x0, y0, and z0, it has one of the planes from this bundle as its tangent plane. So now let's make some comments, some remarks. Now, first, of course, if you look at this equation and z equal constant, since we have in the equation first derivatives, z equals constant is a solution. It is a trivial solution that we are not interested in, right? Because constants we differentiate, we get 0. And second, assume that if we have a solution, right, an integral z equals psi of x, y integral of equation 1 in the domain D where our variables x and y are changing, and assume that this psi is between a and b, and this is not a restriction because we include the case when a is negative infinity and b is positive infinity, right? And then for any continuously differentiable function g, depending on parameter u, on the interval where u runs between a and b, a composite function h, which is g of psi of xy, is also a solution, also an integral of equation 1. And similarly, we can say that if we have a bunch of functions psi1, psi2, psi_m, they all are solutions or integrals of our equation 1 in the domain D, and consider function g that depends on m variable, and this is also an arbitrary function defined on our psi k from 1 to m, and it's such a function that first partial derivative of this function continues. Then we can create another composite function g that depends on psi1, psi2, psi_m, and this function also will be an integral or solution to equation 1. And for instance, we can think of linear combination. If psi1, psi2, psi_m are solutions, then linear combination with arbitrary constant and a1, a2, am also is an integral of equation 1. Let's make another remark. So remark number 3. It turns out that solutions of such equations, linear homogeneous equations into variable, are first order equations, are defined by by integral curves of a system of ODE. So how we can illustrate that? So indeed, consider a solution to our equation. So the plane, the surface that we discussed before, z equals psi of x, y. And then consider a plane, z equals constant, somewhere here, right? So we consider a plane. And when the plane intersects our surface, we will get a curve somewhere here, right? And this curve, so z equals constant, z equals psi of x, y. When they intersect, we have a curve with equation psi of x, y equals constant, and this we know those curves are called level curves of our function. And so this is our level curve. And then if we just project it on x, y plane, we will see that we can make a notation here that x equals phi1 of t is a parameter, and y equals phi2 of t. And so this would be equations of the level curves. X equals phi1 of t, y equals phi2 of t, and z is a constant. And functions phi1 and phi2 are continuous, and their first derivative are continuous. And those functions are such that when we compute our solution psi on this function phi1 and phi2, we are getting a constant, right? That's what we explained. And then let's differentiate this later equation with respect to t. T is our parameter now, right? So we differentiate, and then it will be chain. We will use chain rule. We differentiate psi with respect to first argument psi x, evaluated at on phi1 and phi2 times d phi1 with respect to time, so this derivative with respect to time, plus derivative with respect to the second argument, evaluated at phi1, phi2, and times derivative of phi2 with respect to t with respect to this argument, and then we will have 0. And then our equation, our main equation, can be written this at f psi x, right? Since our solution z equals psi x plus g psi y equals to 0. And then we can write this equation just plugging in phi1 and phi2, and that would be f at phi1 phi2 times psi x plus g phi1 phi2 psi y equals 0. And of course we assume as before that both f and g and psi y and psi x, they are not equal 0 simultaneously. That's why I put here that modulus are positive. And then from these two equations we can solve these two equations for psi y, psi x. Say if we express from this equation psi y and then plug into the first equation, we'll get this, and then we can pull out psi x and assuming that it's not 0, we can conclude that this expression is 0. So what we got is that phi1 prime, derivative with respect to parameter, times g minus phi2 prime times f is 0. And obviously this would be true if we assume that phi1 prime is f and phi2 prime is g, right? If we plug it in here, we will get phi1 prime phi2 prime minus phi2 prime phi1 prime. We will get 0. So so what we can conclude from here? So we can conclude that our projections onto x or y plane, they do not depend on a specific solution on a specific on psi, right? They do not depend here on psi. They depend only on f and g. So they will be the same for all of the solutions, and that's basically the main idea, that based on that we can infer that to find integral curves we have to solve these two equations. Let me write. So to find integral curves, we have to solve equations x prime of t equals f of x, y prime of t equals g of x, y, and and that will give us projections of level curves of a desired surface, and then we lift those curves onto the appropriate height so that they form a continuously differentiable surface z, c at x, y.